Good morning, good afternoon, good evening, mammals. This is for NTI Day number 9, Tuesday, March the 24th. We're going to be talking about what is sadly going to be a virtual lab for us, but I think it's going to be relevant to your AP exam based on my readings of the tea leaves that have come out right now. The College Board is saying that they're going to try and pick questions that are difficult for you to Google answers because obviously everyone is going to have access to Google. There's not going to be any stopping that. So I'm suspecting they're going to frame questions more in lab type scenarios that don't lend themselves to be easily searched up as kind of like fact check sort of answers. So it sucks for us that we're not going to be able to carry this one out in house. But we'll do the best that we can, and there's a good PhET lab that makes it pretty easy. This relates to kinetics because what we're going to be talking about is a procedure where we measure the appearance or the disappearance of a color, and we can use that to study how quickly a reaction happens by looking at how quickly a color appears or disappears using a piece of equipment that's called a spectrophotometer, also known as a colorimeter. And basically what it does is it measures the absorbance, or sort of the flip side of that, the transmittance of light through a sample. The absorbance or transmittance can be related to concentration using what is known as Beer's law. Basically, we're doing kind of a pool test kit sort of thing here. You make a reaction that makes a color appear, and you look at how light or how dark that color is and relate it in some way to the concentration. So, let's dig in. Apparently, I have two of these slides. So, the Beer's law is what we're going to be using. It's also known as the Beer-Lambert law, which is also known as the Beer-Lambert, I'm going to mangle this, Bouger, Booger, whatever. Weirdly enough, he was the guy that first discovered this relationship, looking at how red his red wine was. Then this guy came next and developed a similar sort of relationship. And the most common name of this, after August Beer, was actually sort of the last dude to independently discover this. Whatever. The principle is pretty simple, and it's that there is a direct relationship between the absorbance of light and its concentration and the light's path length. So we've got this equation here. I believe it's on your formula sheet. Absorbance, A. This little epsilon here is just a constant. Different materials absorb different wavelengths differently. So this would be experimentally determined, and it just basically is whatever number is needed to make this work out. It's just a fudge factor, pretty much. You won't have to worry about that. What you will be worried about is concentration and L, or path length. As the concentration goes up, color gets darker, absorbance gets higher. If you make the path longer, now more light's going to be absorbed because it has to pass through more stuff, so absorbance also goes up. So it's a simple, direct relationship. Concentration goes up, absorbance goes up. Path length goes up, absorbance goes up. Easy peasy. And we would measure this absorbance using the aforementioned spectrophotometer. I'm going to give you kind of the inside schematic of how these work. Basically, they have a light bulb which passes through a prism. The prism can be adjusted so that you're only passing through one wavelength of light. And we'll deal with how we select which wavelength of light here in a moment. Passes through your sample in a little square piece of glass that's called a cuvette, and then the detector picks up how much light makes it through. So the absorbance is the difference between how much light came out of this and how much light makes it to that. So kind of a simple piece of equipment. Getting on to selecting the wavelength, the absorbance is not equal across all wavelengths. So I've got a a sample absorbance spectrum here of two substances. So you can see that at some wavelengths of light, there's very little absorbance. At other wavelengths, there's a lot of absorbance. So you would do this with your sample before doing the experiment, and you would test and find where you get the highest absorbance. That's generally going to be your best wavelength to set because your instrument is going to be the most sensitive here. So if you pick something down here, you would get very little absorbance, even if the substance was very concentrated, just because it isn't absorbing that color very much. It's transmittent or translucent to that color. If your sample contains more than one thing, you should also stick away from wavelengths where both of them absorb significantly. So for tryptophan, pretty much anything from 270 to about 290 here would be good wavelengths to measure tryptophan alone because you have lots of absorbance. But if it's mixed with this other substance, uracil, you probably don't want to use anything from 280 or below because now your absorbance in your unknown sample, is it coming from the tryptophan or is it coming from the uracil? You wouldn't know. So if you wanted to test only for the tryptophan, you would probably be wanting to pick something like about 295 here because the uracil doesn't absorb. So you'll be looking for where you get high absorbance, and if it's a mixed sample, you'll want to pick an absorbance that is independent of anything else in the sample. What's kind of curious about this, and I could dive into this, I won't for the sake of time, is that if it's a visibly colored solution, the color that usually absorbs the best is going to be opposite it on the color wheel. And if you think about that, the reason something appears blue to me is because it absorbs all the stuff other than blue. So if I have a blue sample, I'm probably going to be finding peak absorbances in the orangish region. This is not universally true, but it's kind of a good guideline. So once you've settled on your wavelength, you're going to create a calibration curve. And this is just making some standards that you know what their concentrations are and measuring their absorbance so you can get that linear relationship that we talked about earlier. Then, when it comes time to measure your unknown, you put the unknown into the spectrophotometer, it tells you absorbance, and you can come over here and get concentration. Some error things that the AP likes to ask about this. The AP likes to ask about if the kid uses the wrong wavelength accidentally partway through the experiment. Generally, if you use the wrong wavelength, your absorbance is going to be too low because you should have chosen like the maximum absorbance. So if you accidentally set the machine here, now you're going to be getting a much lower absorbance than you think you should be getting. So too low absorbance, too low concentration. I've seen some really weird questions where the kid just didn't dilute the concentration or the standards in the calibration curve. So instead of getting like a nice linear line, one of them's like down here. So obviously that just doesn't fit. And that's kind of a dumb question. Basically, the kid put too much or too little water in it. Whatever. And the one that seems very popular is getting your grubby little fingers on the cuvette. And so the deposits from the oil in your skin are probably going to absorb some light. And so now you're getting absorbance from the unknown sample and from your fingers. And so the absorbance is going to be too high, and so you're going to calculate too high of a concentration. So wrapping up here, what you'll be doing for your NTI is I've prepared a sort of a walkthrough thing for a PhET lab where you're using a spectrophotometer to develop a calibration curve after you've figured out the peak absorbance. And how this relates to kinetics is we would put something in a spectrophotometer, be measuring the absorbance, and we would be watching the rate that that absorbance disappears. And we could see, is it first order, is it zeroth order, or is it linear? Because this absorbance is going to be directly proportional to the concentration. And so that's kind of the end goal. I also included a link to a video. It's a short video, and you can basically see a similar version to what we would have done in the lab. And so that would be good to watch it, because I strongly suspect that your questions aren't going to be this sort of factual information alone, but are going to be, have you been exposed and have you been doing some chemistry? So give that a watch, even though you don't need it to do the PhET lab. So I'll wrap up there. As always, take care of yourself and others, practice good hygiene, and I'll see you on the flip side.